All right, here we are at the final installment of our deep dive into Windows internals. This has been an amazing journey through the definitive guide to the OS, a book written with help from the actual Microsoft Windows team.
So, for this grand finale, we're going to zoom way out. We're taking that 30,000-foot view to really connect all the dots, to tie together all the core concepts we've explored in this series that make Windows, well, Windows.
And you know, when you think about it, we're talking about a system with such a long and storied history. It's evolved from that very first NT release way back in '93 all the way to the OS we all use today. It's really a story of constant innovation, all built on this incredibly stable foundation.
So, here's the roadmap for our final tour. We're going to connect the dots on the core architecture, what happens when a program runs, how memory works, how it talks to hardware, and of course, security. So let's start with the absolute foundation of it all.
Okay, so at the heart of literally every modern OS is this one huge architectural decision. You have to separate the powerful, privileged stuff from the everyday user applications. And this isn't just some casual design choice. It's the absolute bedrock of system stability and security.
This separation creates this crucial protective barrier. So you've got user mode. This is where your browser, your games, your text editors, they all live here. They can't just go and talk to the hardware directly. Then you have kernel mode. Think of this as the VIP section for the operating system's core. It has the ultimate power to manage everything.
And this line right here, this simple line, you could argue it's the single most important concept in the entire Windows architecture. For any app in user mode to do anything important, like read a file or send data over the network, it has to ask for permission. It has to cross this boundary through something called a system call, basically asking the all-powerful kernel to do the heavy lifting on its behalf.
Okay, so that's the blueprint. But how does an actual program, something as simple as Notepad, actually come to life and run? Well, it all starts when it becomes a process, which is basically a container for all of that program's resources. Let's see how that container gets built.
So you see, creating a process isn't just one thing. It's this really elegant dance between user mode and kernel mode. It kicks off with a simple request up in user mode, which then makes that system call we just talked about. The kernel takes over, builds the foundational process object, and then it creates the first thread, which is what will actually start running the program's code.
And that right there, that isolated container, is why your whole system doesn't just crash when one app decides to act up. If Notepad crashes, the kernel can just clean up that one container without messing with your browser or anything else. It's this compartmentalization that makes modern Windows so robust.
All right, so we've got our processes, each in its own little bubble, but here's where the real magic kicks in. Every single one of those processes is tricked into believing it has the computer's entire memory all to itself. And this is, of course, a very powerful illusion created by the memory manager.
So what's the trick? Well, the program isn't seeing the real memory. It's working with its own private map of virtual addresses. Then, behind the scenes, the CPU and the memory manager are constantly working together, translating that virtual address into a real physical spot on your RAM chips. And the application has no idea this is even happening.
And this whole system, this virtual memory illusion, is what makes multitasking feel so seamless. It lets the operating system intelligently shuffle data around, moving stuff you're not using right now out of fast RAM and onto the slower disk. That's how you can run way more apps than you could ever physically fit into memory.
Okay, so a process is running in its own little memory world. That's pretty useless if it can't, talk to anything, right? It needs to be able to read your keyboard, write to the screen, or save a file. And that's the critical job of the I/O system.
So when your application calls a function like read file, the I/O manager in the kernel steps in, it takes that request and wraps it up into this neat little package called an I/O request packet, or an IRP. Then it sends that IRP down a chain of device drivers until it gets to the one that actually knows how to talk to your hard drive.
The real genius of the system is just how incredibly flexible it is. This layered packet-based approach is why you can plug in almost any device you can think of, a mouse, a new graphics card, whatever, and as long as there's a driver for it, Windows just knows how to talk to it. It's what makes the massive PC hardware ecosystem possible. All right, so we've got processes, they've got their own memory, and they can talk to hardware. But wait a minute, how do we control who gets to do what? How do we stop some random program from just deleting critical system files? Well, that's the vital role of the security subsystem.
It really all comes down to two things: who you are and what you're allowed to do.
Every user and every group has a unique security ID, or SID. When you log in, every process you start gets an access token, which is kind of like a security badge that lists all your SIDs. Then every file or object has a security descriptor with an access control list, which is just the list of rules saying which SIDs can do what.
Okay, so let's put all those pieces together with a really common question. You double-click a file, what actually happens from a security point of view? Think of the kernel's security reference monitor as the bouncer at a club. It takes your process's ID badge, the access token, and compares it against the file's rulebook, the ACL. It goes down the list and checks for any deny rules that match you first. If it doesn't find any, then it looks for an allow rule. The very first match wins and the decision is made. It's a simple algorithm, but it's incredibly powerful.
So once you start to understand all these pieces, the user/kernel divide, processes, memory, I/O, security, you suddenly have this incredible power for debugging and performance tuning. But as they say, with great power comes great responsibility, and the authors leave us with a really critical warning.
And this is maybe the most crucial takeaway from the entire book. This knowledge is for understanding, not for exploitation. It's for debugging and analysis, not for building software that depends on undocumented tricks. Because those internal details, they can and they will change with any update. And if your app relies on them, it's going to break.
And that's a wrap on our grand tour of Windows internals. This intricate dance between all these different components has really defined computing for decades. As we look to the future, the really exciting question isn't just how these components will keep evolving, but what totally new ideas might come next. Thanks so much for joining us on this series.
If you want to help me out, please smash that like button, leave a random comment and subscribe if you want to become a better hacker.